Okay, it's recording. Thank you.
Great. Okay. Right. So let's start with your questions. As I say, we're gonna start every TD with question you may have, either on the class, on the document, on the exercise. So feel free to take the lead, unlock your mic, and ask your question if you have some.
I was actually confused if the exercises we had to do were the 3 exercises EC1 or the actual exercise booklet, like the
No.
TD
Concerning
exercise.
the exercise booklet, we are doing this exercise together, more or less. But each time I give you some pages to read on the lecture document, then through this document, you will pass through form tests that you have to do.
Yeah, so the ones that are on Moodle.
Exactly.
Okay.
Exactly. Concerning the exercise, this is what we're going to do during these Zoom sessions, more or less.
Okay, thank you.
So, questions? Everything was clear?
I have a question.
Yeah.
Well, the booklet is in French, so it's kind of in French. But when we look at the courant électrique,
You should have the. I send you the booklet in English, or is it?
Oh yeah. Yeah. I don't have it right now, but
But just for me to be sure that the one I put on. Yes or no?
Yes, it's the English one, but we have the French one in printed.
Okay. So the thing is, I don't have the French one in front of me, but yeah, just go ahead.
So with the electric current, it says it's created by fixed charges. And then it says that the movement of the charges is called electric current, and I don't get it.
Sorry, it seems that I have a poor connection. Sorry, I didn't hear you well. So you said that you didn't catch this, the definition of the current, the fact that the charge are considered fixed, and then when we discuss a current, it's moving. That's it.
Yeah. Yeah.
Okay. My connection seems not good. Is it better now, or it seems that you have some problem? My Wi-Fi is.
I mean, you have frozen up a couple of times, but right now you aren't. But apparently some people can't see or hear you.
So let's see. Have to move. It's gonna be a bit harder. Let's change. And put this here. There you go. So from here, if I just, sorry. Okay, now it should be at least super stable on my side. Is it fine now?
Yes.
Okay. The problem is that I don't have any more a blackboard behind me, but I will do my best. So back to your question about current and moving charges. In fact, when you take a wire, there is no current flowing through it. You just take a single metal wire, but you have this free mobile charge, which are electrons on metals, that maybe move because of an electric field you apply. Which means that if you're not doing something special on this wire, there is no current flowing through it. Charges are available here, but they are just moving like this on their own because of Brownian motion, but they are not like following a specific direction. As soon as you apply a voltage, a difference of potential, then because of this difference of potential, you are inducing an electric field. And as soon as you create this electric field, this mobile charge are gonna feel this electric field and follow this electric field in the same direction or in the opposite direction, depending on the sign. And that's what creates a current. Am I answering your question? Is it clear enough now, or do I need to?
Yeah, so the charges are moving.
At the very beginning, they are like, I think it's detailed a bit. Sorry, I need to optimize my setup at some point. So I think it's explained page 5. The thing is, if you just consider one charge, let's say there is no electric field apply, like any particles, because of the temperature, move on their own. It's called Brownian motion. You can check on YouTube. You have super nice video of particles moving on their own just because of temperature. This is called random motion, and this is the case also for electrons. They are moving on their own. It's completely random. It's actually in every direction, isotropic. So if you take an average of this motion, in fact, it's like they are not moving. They are fixing. Okay, they are more or less fixed. But now, if you want to create a current, then these charges that are available through your wire, you apply the electric field by applying a difference of voltage. You fix this electric field, and then you start seeing your charges moving, which are going to create a current.
Okay, thank you. Yeah, that's clear.
Okay, cool. Other questions?
I have a question.
Yeah. I can't hear you well.
In the
Yeah.
test form,
Yeah.
in the exercise 2, we have to calculate intensity for electrons, and the result is positive, and I don't understand why.
Let me check. Exercise 2, yes. the thing is, well, as you have learned on the booklet, in fact, when we discuss currents, and especially the sign of the current, it's a bit arbitrary. Okay, you don't know when you have a circuit in front of you exactly in which direction the current is flowing. So, except if it's given in the exercise, you are gonna fix it, give a specific direction to your current. So, in fact, more or less, you can say that it's positive. So if it's just a question of sign at the end, and if it's not, which is the case in exercise 2 of Form 1, if we don't give, we ask you what is exactly the sign of the current going through one point to another point, which actually give a specific direction, then you can say that your current is positive. Is it clear or not?
Yes, thank you.
Okay. Other questions?
I also have a question.
Sure.
I didn't really understand what is J exactly.
So the current density, that's what you mean?
Yes.
Okay, so in fact, the density of current is actually the current. So in fact, you take whatever material, whatever surface. So let's say that you have a wire and you cut this wire. So you look through the section of this wire and you get a cycle, a disk. Then you look how much current is flowing through this section, and then you get the current density. That's why, in fact, the current density, the units of the unit of the current density is amp per meter square, which is surface to power 2. Is it better?
Yeah, it's better. Thank
Okay.
you.
Other questions? Sounds good?
What are amps exactly?
Good questions. So this is more or less a definition. So if you go back, I think it's actually said is it expressed in your booklet? I think so. So amps refer to the intensity of the current, and that's it. So when you discuss currents, even when you're at home and you're looking at how the current is flowing through your house, your apartment, then you have two main parameters, which are voltages and current, and also the frequency, because, well, this is we're going to discuss this during the next part of electrokinetics. Right now we are discussing with the steady state. Steady state means that we are only discussing equilibrium, no transient state, which means that we are waiting long enough for the system to be equilibrated for a long time. And the other thing is the source we are using only deliver continuous either voltage or intensity, which is not really the case when you plug your computer to the electric power on your house. Okay, you have an extra voltage you have to consider. So in fact, when you look at the shape of the intensity flowing through your house, it's not straight, it's like wavy because of this frequency. All right. Sorry. Oui. Oui, cours. Je suis en cours. Désolé. So yeah, just take amp as a definition, just the units of the current flowing through your circuits.
Okay, thank you.
Other questions? Fine, is it okay? Okay, cool. So back now to exercises. So today we're just gonna discuss more like a general thing, considering formulas. We are discussing dimensions and more or less units. It's quite important and it's gonna help you a lot in physics. Well, anytime you're gonna use a formula, more or less, especially with physical parameters, I would say. It's a way for you to double check if your result is correct or not. So have you ever heard about dimensions, dimensions equations? Is it something you use?
We saw this in mechanics because we also have to take care of dimensions.
Okay, so I'm not gonna teach you something right now, or do you want me to just remind you a few things, or is it fine? Can we just go directly straightforward in the exercise?
I think a reminder would be great, please.
Okay, so discussing about dimension, you know that every formula, every unit can be expressed through what we call dimensions. You have, in fact, 7 different dimensions, which are mass, length, time, intensity, temperature, I don't know the...
Lumen?
Yeah, lumens,
Right?
yeah.
Lumen.
Yeah, lumens, and quantity of matter. That the 7 dimension you are allowed to use when we discuss dimension, which means that each time, let's say we are discussing resistors have specific resistance, but resistance, the units of resistance is ohm, but ohm could be expressed with these 7 dimensions. And this is the case for every units. And so when you write a formula and when you write a result, you need to be sure that it's homogeneous, which means that the final dimension is what you're looking for. And this is here just a way with this first exercise, just a way to remind you this and train you on using this dimension to try to express what are or to convert a unit into dimension, to be sure each time you have a result that it's homogeneous and it corresponds to the right dimension. Is it clear for you?
Yes.
Okay, great. So now you are, we are moving to the exercise booklet, and so the first thing is, so you have in front of you the booklet on exercises. First exercise, units used in electronics. We are not going to do the full exercise. Why? Because some of the units and dipole discussed in this exercise will be only introduced in the second part of electrokinetics. So right now you don't have all the information to finally, to correctly do the full exercise. So let's just discuss the first part. First question, the dimension of electric field, voltages, and resistance. All right? So go ahead and try to find the dimension of an electric field. So if you want to solve this exercise and try to find this dimension, you should find, in fact, formulas where the electric field is involved. So try to find formula where this electric field is involved, and then through this formula, try to express every parameter of this formula into dimensions to get the final dimensions of electric field. I give you, like, let's say 5 minutes. Take a draft, take some pen, and try to discuss how can we handle this electric field thing and get its dimension. All right. As soon as you have a result, feel free to tell us. So first thing to do, find a formula where we are using the electric field. And I think you don't know much of them. I'll be back in 1 minute. So which formula are you going to use with the electric field?
Maybe that a charge going through an electric field makes a force.
Exactly. So that's the Coulomb force. F equals to Q time E. So this is your starting formula. Then the problem is, well, you have the force, but what are the dimensions of the force? You know the units of the force, which is Newton, but Newton is not a dimension, it's a unit. So now you need to find the dimension of a force. Maybe you know other formula where a force is involved. Let's think about a basic one.
Like the weight.
Like the weight.
So we have the mass times the gravity. So
yeah, that's a good hit. Another basic one will be Newton formula, which is the sum of the forces equals to mass time acceleration. And with this, you can now have directly the dimension of the force. So F equals to m times a. So the dimension of the mass is a mass, it's already a dimension. Then you have to find the dimension of an acceleration. And you already know it.
Length and time.
Square.
Yes.
So it's L times t power minus 2. That's the dimension of the acceleration, which means that at the end, the dimension of a force equals to m time L time t power minus 2. Is it okay for everyone? Right now, maybe if I can try to connect these tablets. Just let's see if I can do this. So now you know the dimension of a force. Then you need to find the dimension of a charge. So what are the units of a charge?
Coulombs or
Yes.
amps times time.
Okay, so back to coulombs. What is a coulombs? So in fact, if we go back to the definition of a coulomb, it's the quantity of electricity, of current, flowing through a conductor if you consider 1 amp per sec. So the quantity of charge that you see through a conductor, if there is a current of 1 amp per sec. So at the end, the dimension of a charge is just intensity, which is amp, time. I'm going to try to connect maybe because I don't have any blackboard here, and I just see here how this is working. If I get this, so with this you should end up with the final dimension actually of what we are looking for, which is the electric field. So you know that F equals to Q times E. You know the dimension of F, you know the dimension of Q, so you can deduce the dimension of E. And by that time, I'm gonna try to connect, maybe not, this tablet. I hope I won't lose the connection. See. Yes, seems to work. So let's see. Because if now I can work here. No, I miss something else. Yes, okay. Maybe I can use my tablet. It's not super functional, but let's see. If I in data, and if I all right, so if now écran partagé. Here we go. Could you see my writing?
Yeah, well, we can see.
Right now,
Yes,
should we?
we can.
Yes.
Cool. All right. So back to, so we got, man, I have to get used to this. So we get F equals to Q times E. All right. We said that F equals to M times A. So back to dimension. So when we discuss dimension, one way to do is to use brackets. So the dimension of M is mass time so it's a length time t minus 2 for time power minus 2. All right. Then so we said that charge. So the dimension of a charge equals to intensity, so time t. So now with these two equations, you can go back to the dimension of E. And I leave you the end of this.
I have a question.
Yes.
Can we put an arrow over the length in brackets?
No. Well, in fact, the way of writing this into brackets is just that I'm using dimension. So this is, well, no, you're right. I should, how can I write this correctly? Normally, when you discuss dimension, you have to put everything into brackets. So when I write this, I say, what is the dimension of E? And E is a force. So I put an arrow on it, all right? So each time I'm using brackets, it's just that I'm considering dimension.
Yes, but even if we only consider the dimension of a length, it also has a direction, so we could also put an arrow over it.
About what? About length?
Yes, L. We have M times in brackets
Yeah, but
L.
this arrow doesn't correspond to a direction. It corresponds to a force. That's why I'm not putting an arrow on top of L.
Okay, I didn't understand that. So,
okay.
Thank you.
All right. So this, well, in fact, to say that it corresponds to a force, either I put an arrow, or sometimes in documents, in books and else, it could be written in bold. Bold mean force, mean vector. Do you get that?
It means that we're using the dimensions if it's bold, or
No,
don't-
bold means that it's either you use bold or you use an arrow on top of your parameter.
oh, okay. Oh, okay. So what you've done in bold wouldn't have the arrow on top.
Exactly, exactly.
Okay. Okay.
So you finally got the electric field dimension. Someone can give me the final result? What is the final dimension of the electric field?
I have m l t minus 3 I minus 1.
Is it okay for one? So I should put brackets, of course. All right. Is it clear, or do you have question on the concept, more or less?
For me, it's okay.
Okay. Everybody is fine?
Yes. Yes. Very much.
Okay, cool. So can I move to? Yes. All right. I get used to it. So now we have the dimension of the electric field. The second question is what we ask you is to get the dimension of a voltage. So voltage, the units is volt. It's written V. But what is the dimension of volts? So the trick here is to consider that the units of the electric field. Do you know the units of an electric field? Or do you know how to create an electric field? I already told you how to do previously.
We take two different voltages on different places. So it's
Exactly.
a difference of voltages.
Exactly. So a certain voltage is here, another voltage is there. Then you have an electric field. So in fact, since it's a difference of potential, and a potential is also expressed with voltage, then the electric field, the units of an electric field is volt per meter. And you already know the dimension of the electric field, right? So with this, you can deduce the dimension of a voltage, which is just the dimension of E, time. Here it's per meter, so here it's a length. Do you get that?
Yes.
So back to the dimension. If I just multiply the dimension of E with L, I get something which is this. And of course, I should put everything into brackets. Okay?
I have a question.
Yes.
When I tried to do this, I used the power, which I think is the intensity times the voltage, and I think I did a mistake because I can't find the length squared. I just find length.
So you were saying that power, right, is well, actually the voltage time a current. That's your point, right?
Yes.
So what is the dimension or the units of power. It's what?
Kilograms meter squared times, sorry, m t squared, sorry, ml squared t minus 3.
Are you sure of that?
Yes, I forgot the squared by L, sorry,
So,
in my calculations. So I understand now.
so now it should be fine, right? Okay. Is it okay?
Yes.
Perfect. So last question is about the dimension of a resistor. So from now, the only formula you know that is
Sorry,
yeah.
can you explain again why the dimension of E is equal to V over the length?
Yes. So we were discussing the definition of an electric field. An electric field, which is E, is generated if you put, let's say, two electrodes with different potential, and you put them at a certain distance. So when you have, let's say, and it's exactly the same when you consider a point where you have like a lot of positive charges and another point where you have other negative charges, then you do have some electric field between these two because of a difference of voltages. Here, let's say you have here a potential of plus V1. This potential, the unit of this potential is volts. And here you have another potential, let's say it's minus V2. Okay. Then the voltage is a difference of potential. V2, well, let's call it V2, but we say that it's minus because it's composed of minus charge. So it's V2 minus V1. So a voltage is a difference of potential, and potential is in volts. And how to create an electric field? You put a difference of potential and you have a certain distance between them. So in fact, the units of an electric field is a difference of potential over a certain distance, a length. This is how I end up with these units for the electric field.
Okay, that's clear. Thank you.
Perfect. So now, next question is, what is the dimension of R? For now, the only formula you know using a resistor is the famous Ohm law. And that's more or less one of the unique or single formula we're going to use in this first part. So you absolutely need to know and understand this law. So when you consider a dipole, which is a resistor R, you have a certain voltage and a current flowing through this dipole. Then you can tell that the voltage equals to R times the current. And you can now deduce the result of the dimension of R, which is going to be the dimension of U over the dimension of E. And I give you just an extra 5 minutes to get the result. If someone already has the result, please let me know.
We have it.
Okay, I'm listening.
We have m times L2 squared times e to the power minus 2 times t to the power minus 3.
Okay, perfect. All right. So yeah, everything is recorded, so you can already have the results, and we can move further in the next exercise. So for question B and C, as I say, we're not going to discuss them because they introduce other dipole, which are capacitor and inductor, and that the two dipoles you're going to see in the second part of electrokinetics. Right now, we're not introducing them. So just to let you know that you have to pay attention to dimension and formula, and it's gonna take you a few minutes to double check at the end of an exam if all your formula have the good units and if your formula are homogeneous or not with this practicing. So that's a good thing to do. Take a few minutes just to double check, because it may it's a good way for you maybe to discover some issues or some typos you may have done during your computations. All right.
Excuse me.
Yeah.
I don't understand the difference between U and V.
There is a difference. Next, please. So U is a voltage. V is a potential. The voltage is a difference of potential. But, and this is where the confusion is starting. So let's say that you have an electric circuit, a resistor, then you have the mass, and here you have a certain voltage at 5 volts. All right, this point is at 5 volts, and here it's the mass, hertz. So it's, sorry, in English it's ground. So V here equals to 0. Okay. So then you have this voltage here. Let's call it U1. So U1 equals to the difference between these two voltages, which is V5 minus V0. Okay. The problem is V0 equals to 0. So at the end, U1 is only V5, so it's only 5 volts. That's where the confusion starts. Why? Because in fact, U could also be a V, just because this V0 equals to 0. So sometimes in the exercise, you might see a V, which is actually a voltage and not just a potential at a point. Am I clear or not?
Yes.
Okay. Okay. So that's the main difference, but this is quite important to understand. Do you have other questions, or can we move to the next concept? I'm not checking the discussion things, but I don't see if someone asks some question by writing something, but I hope not. All right, so we now move on to the next part, next exercise. And we're going to start by playing with dipoles, and the only dipole we're going to play with during this first part of the lecture is a resistor. So I'm actually anticipating a bit the lecture documents. So I'm going to try to start to explain you some concepts. And for the next time, of course, you will read this concept back in the booklet. So it might be helping you to understand maybe better, I hope. So we're going to play in this part of the class with resistor, with a voltage generator, and with intensity generator. Depending on professor's book, country, sometimes it could be, I would say, defined with different schematics. So all of these are purely identical. This is just other way of defining resistors. I'm missing something. Let's see. No. That's it. And the idea in this lecture is try to combine all of these components in a circuit and see how the currents and different voltages through the circuits are going to evolve and change, and how can I calculate them easily. So let me introduce you just these two component here. A resistor is just a passive dipole, but it's really, I mean, you find resistor everywhere. This is how you cook your pasta at Pomology. In fact, because you eat you make your water boiling because of the Joule effect. Which is flowing a high current through a resistor. And because of this high current flowing through your resistor, it's gonna generate some heat that may be used to boil or eat whatever you put on it. So this is the only dipole we're gonna see, and then we're gonna see two generators. This generator have some characteristics. As I say, in this class, we're gonna discuss continuous or steady state position, which means that over time, the variation of there is no variation of voltage and no variation of current. So let's say I'm using a voltage generator, which means that if I put it in a circuit and plug a resistor, whatever the current here flowing through this generator, the voltage, I get it here, is constant. And it's fixed. I can say that this generator is delivering 10 volts. And if I put something else here, if I increase the resistor or whatever, then the current here is going to change, but the generator is going to adapt itself to deliver always the same value of the voltage, whatever the current. And for the intensity generator is exactly the opposite, which means that whatever the voltage that I consider, I'm going to adapt this voltage to deliver always the same current. Is it okay?
Yes.
Yes.
Okay. So now, how can we battle, or I would say, how can we play with this dipole and connect them into circuits? So let's first forget about generator and just focus on resistor. So you have only two ways of plugging resistor. Either you put them sequentially, which means that you have, well, a dipole has two terminals. Okay, so if you put them in the same line, in the same row, which means that the same current is flowing through both of them, it means that these two resistors are in what we call series. First way. Second way, we can join their terminals. So this is the two terminals of this resistor, but at the same time, I'm plugging on the same terminals another resistor. This time, the two resistors are in parallel. Maybe there is 2R, I don't always confused about this word. Okay? And here, the thing is, they are in parallel because the current that is arriving at this node is going to be divided into I1 and I2. And that's where I'm going to start playing also a bit with formula. You know that U equals to R times I, which is what we call Ohm's law. Then the other formula, which is important, it's what we call the node law, which is, let's take a node. A node is just a point where you have few connections that meet. So I have a node here. I have entering currents. And I have other currents which are flowing out from this node. And there is what we call a node law, which is the sum of the currents entering that I'm going to call input currents that are equals to the sum of the currents that are going out from the node. In that case here, I can say that E equals to I1 plus I2. Okay. And the other important formula we're going to play with is a formula called mesh law. Mesh law, which means that a mesh is a link, an association of dipoles that are forming a closed loop, and this is called a mesh. And I'm starting from points A, B, C. Sorry. D. So now I can put some voltages. This is UAB. When I write UAB, the arrow is pointing to the A. This is quite important. So this is UDA. This is UCD. And this is UBC. The mesh law is just saying that, sorry. It's just saying that come on, UAA equals to 0. So let's say you start from here and you add this tension, voltage, plus this voltage, plus this voltage, plus this voltage. So you back to this node here, this point A, and it should be equals to 0. So in fact, this is just another way of writing shell law. So this is what we call the mesh law. But this is just another way of another law which is called shell. I don't remember if there is an S or not. Law that maybe you already know from mechanics, maybe. So in fact, UAA is UAB. Come on. UAB plus UCD plus UBC plus that's it. CA, sorry, CA. What I wrote. And that's it. And that's only what I'm going to use to deals with these circuits. Then later in the lecture, we're going to see different theorems that are going to ease our life to, it's every time based on these laws, but it's another way of using them. And it's going to help us solving and simplifying our circuits very quickly. All right? And that the main formula we're going to play with in this lecture. Do you have questions for now?
No, not me.
Okay, seems clear. So this is kind of an overview, a sum up of the first beginning of this class. And now we're going to try to look at some different types of circuits and try to simplify them. All right. This is what we're going to do in exercise number 2. So, exercise number 2. The idea is, okay, here is no, sorry. Let me say something else before. So back to how to associate dipole together. So I was saying that one way is having them in series, or the other way is having them in parallel. If they are in series, it means that the same current is flowing through them. Okay, but this is equivalent of a single resistor, which corresponds to the sum of these two resistors. So having them in series, I can substitute these two into a single one, and the value of the resistance of this single one resistor is the sum of these two resistance. All right? So that's the case for two resistance series. So now if I consider two resistors that are in parallel, it's a bit different. So here I can say that the equivalent Rec equals to R1 plus R2. Here I can still substitute these two resistors series with a single one. I'm going to call Rec, and this Rec equals to the product of the two resistance over the sum. Or the inverse of Rec equals to the sum of the inverse of the resistance. And then if you simplify this, you go back to this. This is two important formula you have to remember. Of course, you can extend this with more than two resistors. So easy, when it's in series, you just sum them. In parallel, you have to go back to this formula. So you know that there is some product and there is some sum. If you don't remember if here at the denominator it's the sum or if the product, then it's where you go back to the dimensions. Why? Because the dimension here, or I would say the units, would be the dimension of R to the square. And the dimension of R here, it's just the sum, it's R. So the final dimension is indeed the dimension of a resistor. If you did some mistake, and let's say you start with the sum, then you have the inverse, which is R over R to the square, and you end up with R power minus 1, which is not homogeneous to a resistor. So you see just here a single way, quick way to double check if your formula is correct or not. Do you get these two difference between in series and in parallel, and how to simplify them? Or do you have some questions?
No, I don't have questions.
Perfect. So we reach the end of this class. So I'm gonna Sorry, give me just a second. I'm gonna stop this and just give you the outline for next time. Where did I put them? So next time is next Monday, right? So for next Monday, you are gonna be on your own. I mean, you have one session which is blocked Monday morning, but we won't connect. We won't do any session on Zoom. It's gonna be an autonomous session for you. And you're gonna work on the booklets up to page 15. So up to this page, you will learn exactly, it's kind of a reminder of what I just explained you. And when you're gonna reach page 15, by that time you will reach the test form 2 and test form 3 that you have to do for practicing. All right. And for, well, with all of this, next time we will be able to actually and easily do exercise 2 of the booklet together to double check if everything is clear for you about this association of resistors. Is it okay?
Yeah, it's fine.
Yes.
Yes.
Perfect. So have a nice day, have a nice weekend. So we won't meet on a Monday, and I think the next time we will meet is, let's see, I think it's next Tuesday afternoon at 2. So yeah, Monday on your own, and Tuesday we will do this exercise together. By that time, if you have questions, feel free to send me an email. And if not, we're gonna start, of course, the next session with your question and then go through this exercise about association of dipoles.
So we will do the test form 2 and 3 on Monday when we're going to be on.
Yeah, you have this 1 hour for you. It's blocked on your schedule, and then you can use it how you want. So you can use it to go through the booklet up to page 15, to do the test form, to discuss with the member, the other member of your group. But you can do this work during the weekend and have an extra hour on Monday to sleep. You are free. But this is just for you, at least, to get an hour to work on this particular subject. Okay.
Okay, thank you. I understand.